Hi, my name is Ivan Arcuchin. I'm a PhD student from University of Buenos Aires, Argentina. In this video, I'm going to be presenting the paper on the feasibility and challenges of synthesizing executable Espresso tests. My co-authors are Cristian Cicciaroni and Juan Pablo Gagliotti, both also from University of Buenos Aires, and José Miguel Rojas from University of Leicester, UK. In recent years, mobile apps have become more and more important in our daily lives, from web browsers and social media to multimedia and messaging apps. Despite their growing popularity, apps tend to contain defects which can ultimately manifest as failures or crashes to the end user. To avoid this and ensure a minimum quality threshold, developers can manually write test cases. However, this is a very tedious, time-consuming and error-prone task, and hence expensive. Espresso is a popular UI testing framework for Android apps. It provides an API to help developers write concise, reliable, and human-readable UI tests. Multiple automated tools have been proposed in recent years for testing Android apps and improve their quality. Nevertheless, just a handful of those tools target the Espresso format. What is worse, not all of these tools generate test cases in an executable and human-readable format. Therefore, many of them do not shield their test cases in a format that motivates developers to read and modify such tests later on. Thus, in this work, we explore the feasibility and challenges of leveraging existing state-of-the-art tools for generating Espresso tests. We do this by performing an empirical study followed up by an analysis and discussion of the challenges and limitations found. To understand these challenges, we first need to understand the way in which Android UIs are built. Android applications are composed of activities. To define an activity's UI, a developer must provide a view hierarchy, which is a tree with a root view positioned at the top and child views positioned as branches. The view class is a base class for widgets, which are used to create interactive UI components, for example buttons, text fields, etc. This figure shows an example of a UI and part of its hierarchy. The XML snippet describes the layout of each row in the first screen. Now, the Espresso testing framework API is divided into three parts. First, view matchers are used to find views in the current view hierarchy, view actions to perform actions on the views, for example, click, and view assertions to assert the state of a view. This is an example of an Espresso test case that performs a click action on a view with ID button and parent ID activity layout. It is important to note that if the target view was not found or several views match the selection criteria, the test execution will raise an exception. To perform this study, we built on top of the mate testing tool and implemented a prototype with this architecture. We extended mate in order to produce a JSON file describing the sequences of widget actions that will constitute each Espresso test case. Each widget action in the JSON file indicates the type of action performed during exploration, the target widget, its parents, children, and specific attributes if there were any, for example the display text. The algorithm for the Espresso code synthesizer used in our prototype is depicted in the current image. The model translates each sequence of widget actions into an ideally semantic preserving Espresso statement. This is achieved by consecutively synthesizing the code for the appropriate view matcher to select the widget and the corresponding perform operation on the selected widget. As mentioned before, Espresso view matchers expect to match a unique widget within the current view hierarchy. We call this the problem of widget disambiguation. Often, the desired widget has a unique resource identifier which can be used to unequivocally target it. However, there are many legitimate cases in which the target widget may not have a resource identifier or the identifier may not be unique. To mitigate this problem, we use the heuristics proposed by the official Espresso documentation and state-of-the-art literature. For example, using the parent view's resource ID, using the children view's resource IDs, and using the view's text or content description if non-empty. The goal of the empirical study presented in this article is to evaluate the correctness of the synthesized Espresso test cases. This also included a large quantitative and qualitative analysis to assert that the intended semantics of the original sequences are preserved. The following research questions aim to reveal how pervasive this problem is. First, do the synthesized Espresso tests reliably replicate the coverage achieved by widget action sequences? Second, do they reliably replicate the UI states achieved by widget action sequences? And third, which are the most common causes for failure in the synthesized Espresso tests? For the experiments, we use 12 open source Android apps with Espresso setup and previously used in the literature. The modified version of MATE was run 5 times on each subject using a random exploration algorithm. We chose a time budget of 1 hour for each run. Now, this figure shows for each subject the overall coverage achieved by MATE and the synthesized Espresso test cases. The latter achieve a similar coverage to MATE widget action sequences. Although the differences between coverage are small, in most cases the synthesized Espresso test cases achieve lower coverage than MATE. We conjecture that this behavior, which is consistent across many subjects, is caused by the fact that there is at least one failing action on each test suite when executed. So the result for research question 1 is that the synthesized Espresso test preserve over 90% of the widget-based exploration coverage. Now for research question 2, this figure shows the percentage of failing actions and diverging screenshots when running the synthesized Espresso tests. We refer to diverging screenshots as points in the test execution where the original widget-based test sequence and the synthesized Espresso test diverge. That is, when they are in a different UI state. We find that, on average, each test case had 25% of actions fail and 30% diverging screenshots. Given the high number of diverging screenshots found, we decided to perform a more detailed qualitative analysis. Now this table summarizes the causes observed for the diverging screenshots. The main cause observed is wrong UI state, meaning all the screenshots that are different as a consequence of a previous divergence in the test. For example, a failing back action at the beginning of a test case means that the following actions in the test will start from a different UI state than what was intended in the original sequence. This may indicate certain fragility in UI tests, which is a known problem that has been studied in the literature. So, in conclusion, the result for research question 2 is that the synthesized Espresso test achieve similar UI states in about 2/3 of the test cases. In the ones that differ, it is usually caused by a failing action at the beginning of the test. Given the high amount of mismatching pairs of screenshots that were caused by a previous divergence in the test, we decided to also study the first failing action of those tests. This table shows the causes of the first failing action for the test cases we analyze. JSON scheme refers to all the cases in which a failing action could be fixed by enhancing the JSON schema with additional information that is already available in mate. View not displayed refers to any action that failed due to the target view not being displayed in the screen. Here, the behavior of mate collides with the way that the default Espresso actions work, which assumes that target views are always displayed to the user. Wrong info refers to actions that fail due to mate providing erroneous information in the JSON. For instance, actions performed by mate on UI elements outside the application, for example in the top bar of the device, break compilation of the corresponding Espresso tests since the resource IDs of those views are not defined within the target app. Thus, the result for research question 3 is that the most common cause for failures are missing information in the JSON scheme, performing actions on widgets not displayed, erroneous information from mate, and overall flakiness in subjects. Finally, we performed in the paper an analysis and discussion of the challenges and limitations of automatically generating Espresso tests from widget-based test generators. In order to understand the usefulness of tools such as the one proposed for developers and the Android community, we also present the feedback collected from pull requests sent to open source projects and feedback from developers of an industrial app. The main challenges detected in our empirical study is the difficulty to properly indicate to the Espresso framework the view on which it should perform an action. To do so, an Espresso test case generator or developer has to correctly build a corresponding view matcher. Since the Espresso framework requires an action to be performed on an unequivocally identified view, this view matcher must be built with great precision. And failure to do so causes the Espresso framework to raise an exception. This problem is aggravated in some cases by the lack of unique properties to unambiguously identify specific widgets in the UI, and the incomplete or ambiguous definition of UI components and layouts. This points out that further research is needed to find ways to improve the testability of Android apps either manually or automatically. To mitigate this issue, view matchers can be built using resource IDs, although they are not always unique, and many other view properties. For example, the text, the children, the parent views. And these properties may help narrow down the search. Therefore, it is of the utmost importance that the information provided by the underlying test generation tool is plentiful and accurate. Any missing or wrong information has a high chance of causing a failing action. We also found that it is important that the test generation tool performing the exploration executes the actions on views that are reachable for Espresso. For instance, actions performed on views not displayed to the user will not work with Espresso default actions, and as mentioned before, those actions performed on views outside the application will not work at all. Despite the strategies implemented to mitigate the problem of widget ambiguity, some cases might not be possible to disambiguate. For example, images with identical hierarchy but different content. This can happen, for example, if two different images are side by side. In this case, it is not possible to build a view matcher that distinguishes both by the content. Also, widgets with identical hierarchy and content but different siblings in the hierarchy. For example, here the screen shows a short list of beverage options in which each row has the same checkbox, but all the rows have different text. We might want to target a specific checkbox, for example the first one, But if we only look at the parent and children hierarchy, there is no way to distinguish one from another. This might be solved if we add siblings to the JSON scheme, or if we provide the whole UI hierarchy tree in the JSON. It is important to note that using the index of the item in the list is not recommended, since it is common for list layouts to automatically destroy the views corresponding to the items that are no longer visible to the user after scrolling, as a way to gain performance. And then widgets with identical hierarchy, content, and siblings. For example, if we have duplicated rows in a list, identical even including the content, as shown for the pepperoni row in this list, then the only way to disambiguate them is by using their position on the list, but this information, as mentioned before, is unreliable. To understand the usefulness and limitations of the synthesized Espresso test for developers, we evaluated the effectiveness of the implemented prototype on the previously studied 12 open source apps plus one industrial project. We submitted synthesized Espresso test as pull request for the open source apps in which we managed to increase the test suite coverage in the project. Of the 8 pull requests submitted, we received responses with comments for half of them. 2 projects actually merged the pull request into their test code base and thanked the contribution. 1 pull request was closed without comments, and shortly afterwards the project was closed and archived by the maintainer. Our hypothesis here is that in this early stage, the prototype's output is mostly useful for active projects without test cases or with some test cases but low coverage. As mentioned, we also provided the prototype to an industrial partner for its evaluation. After trying out the prototype and inspecting the synthesized Espresso test, they reported the following positive aspects. First, that for the projects with none or few system-level tests, it provides a quick and simple way to increase their coverage. Also, that the generated tests also serve as a starting point for creating new test cases. As negative points, they reported that the synthesized Espresso tests tend to be large and fragile. Also, they do not provide a clear description of what are the goals of each test case. This last point was very important since they reported that a clear description will be needed before including them to the code base. As future work, we plan to explore different testability transformations that might improve the reliability of the synthesized Espresso tests. Besides, it would be interesting to extend other testing tools to perform a similar study using sequences of widget actions that may differ from the ones generated by Mate. Another possible line of future work is to perform an empirical study using other testing frameworks such as Appium in order to evaluate trade-offs between competing frameworks. Finally, we plan to assess and improve the quality of the synthesized Espresso tests in terms of fault detection and non-functional properties such as readability. To conclude this presentation, we conducted an empirical study evaluating the feasibility and challenges of automatically synthesizing Espresso UI tests from widget-based action sequences. The study was carried out on several open source apps and one industrial project. To further understand the challenges and limitations of automatically creating Espresso tests, the study was followed by a quantitative and qualitative analysis of the results. Our prototype implementation and experimental results suggest that leveraging existing testing tools to generate executable Espresso tests is a promising research direction. On the other hand, our study unveils concrete challenges that will need attention before a fully fledged industrial-strength solution can be devised. We believe this work contributes towards bridging the gap between existing Android app testing tools and developers requiring Android tests in Espresso format. Thank you very much for watching.